So today, I will present the general biosensing for rapid detection of SARS-CoV-2. Go to background. The current standard for testing of SARS-CoV-2 is a PCR. PCR benefit from selective amplification of nucleic acid sequence of target gene. However, it has the drawback of long examination time, complicated multi-step analysis, insufficient accuracy, and requirement for skilled operator. If the testing of SARS-CoV-2 is largely simplified and shortened, it will be a powerful deterrent to the spread of COVID-19. Optical biosensor is a potential method for rapid detection of SARS-CoV-2 due to the high sensitivity, cost-effectiveness, versatility, ease of testing, and point-of-care prospect. And one representative is a surface plasmon resonance, or SPR, like here. In SPR, when a monochromatic laser light is incident into the glass prism covered with a metal thin film at the total reflection angle, the induced evanescent wave is coupled with a collective vibration of free electron, namely its surface plasmon. This results in conversion of light energy into the surface plasmon energy. So when a reflected light is measured with respect to the incident angle, the reflected light is sharply decreased at this resonance angle right here. So this is SPR dip. SPR dip shift depends on the sample area via the electric field induced by the surface plasmon. So it enables the sensitive measurement of sample area. Furthermore, if the surface modification of antibody is made on the sensor surface, like here, the antigen-antibody interaction change effective RI. As a result, the SPR can be also used for the optical biosensing. So the remaining challenge of the SPR is that the broad SPR dip and its small shift limits the sensing performance. For the highly sensitive optical biosensing, the real RL-dependent or antigen-dependent optical spectral shift should be transformed into the photonic radio frequency or RF signal with a sharpened spectrum. To this end, we introduced the two keys in optical biosensors. The first key is the combination of the optical frequency cone with a fiber biosensor in the cavity, enabling a photonic RF biosensor or electric frequency reading optical biosensor. The second key is the active dummy compensation of temperature drift of sensor signal by using a dual cone configuration. But why we use the optical frequency cone or OFC? OFC is composed of a series of frequency spikes regularly separated by a constant frequency. OFC possesses both characteristics of narrow line width and broad spectral coverage together with constant frequency spacing. The most important characteristics of OFC is given by this simple equation, where the nu m is the optical frequency of each OFC mode, FCO is the carrier envelope offset frequency, FREP is frequency spacing, and M is the mode number of OFC. Since FCO and FREP are photonic radio frequency signal around several tens megahertz, this equation indicated that the coherent link of frequency between optical frequency and electric frequency. For example, if the FREP and FCO are phase locked to an electric frequency standard by laser control, uncertainty of the frequency standard can be transferred to nu m based on this equation. In this case, the OFC can work as an optical frequency ruler secured by the electric frequency standard. But in this presentation, we replace this electric frequency standard into the optical fiber sensor, like here. In this case, an optical spectral shift of nu m caused by the fiber sensor can be transformed into the FREP, electric signal of FREP, based on this equation. So which is the opposite direction to the optical frequency ruler, namely from optical frequency to electric frequencies. In this case, the OFC can work as an frequency converter or frequency gear from optical frequency to electric frequency. So we applied, in other words, the OFC can be used for the photonic RF fiber sensing, so which is a benefit from electric frequency measurement in the RF region, such as simple, high precision, wide dynamic range, rapid, and cost effectiveness. We apply this concept for optical biosensing of SARS-CoV-2. We here use a multimode interference or MMO fiber sensor, like here. The MMO fiber sensor is composed of a cloudless multimode fiber together with an input and output single mode fiber laser. The incident light is diffracted and repeats a total reflection and go towards the output SMF. So only the light satisfy this equation, so which this is lambda MMI wavelength or lambda MMI can pass through this fiber sensor. Furthermore, the Gauss-Hessian shift at the boundary between the fiber surface and a liquid sample, namely sensing surface, depend on the refractive index of sample. So the lambda MMI is a function of a sample Ri, like here. Therefore, the MMI fiber sensor can work as a Ri-dependent tunable optical bandpass filter. And then, so we next place this MMI fiber sensor in the fiber OFC cavity for conversion of optical frequency to electric frequency. Next slide shows the principal operation for Ri-dependent FREP change. Here, there are two keys. The first key is an intercavity MMI fiber sensor. In this first key, the sample Ri change is converted into the optical spectral shift of OFC, like here. And the second key is dispersion of refractive index in the OFC cavity fiber, like here. So the Ri-dependent optical spectral shift is converted into the Ri-dependent Ri-dependent shift of optical cavity length, or NL. Since FREP is given by this equation, so the Ri-dependent FREP shift can be observed around the several tens megahertz. So in this way, the FREP reading Ri sensor or Ri sensing OFC can be achieved. Next slide shows experimental result for Ri sensing of ethanol water solution. Here we compare the Ri-dependent shift of optical spectrum and RF spectrum. In the optical spectrum, Ri-dependent optical spectral shift is significantly smaller than the optical spectral bandwidth. On the other hand, in RF spectrum, the Ri-dependent optical spectral shift is significantly larger than the optical spectral bandwidth. So this comparison highlights the use of RF spectrum is better choice for sensitive Ri sensing than the optical spectrum. We next make the surface modification of SARS-CoV-2 antibody on the intercavity sensor surface. For the optical biosensing of SARS-CoV-2, we use antigen-antibody interaction of SARS-CoV-2 protein Among the several proteins in SARS-CoV-2, we selected the nucleocapsid protein or N protein because of the abundant existence and the low mutation introducing probability, as well as high specificity, sensitivity, and stability. We made the surface modification of N protein antibody on the sensor surface via the SAM layer, like here. Then the OFC light induced the evanescent wave near the sensing region here. So if the target protein, target antigen come and combined with the corresponding antibody like here, the OFC light is influenced depending on the antigen concentration. We next place this fiber biosensor inside the fiber OFC cavity for the optical to electric frequency conversion. Next slide shows the principle of operation for antigen-dependent FREP change. Here, we further introduce the third key for biosensing, namely antigen-antibody interaction, highlighted by red color. So in this third key, the concentration change of target antigen is converted into the effective RI change near the sensor surface by selective combination of target antigen with the corresponding antibody. Then, so we use a similar procedure to RI sensing. Finally, so change in the antigen concentration is read out as the FREP shift around the several tens megahertz. In this way, so we FREP reading optical biosensor or biosensing OFC can be achieved. Remaining challenge of biosensing OFC is the temperature drift of sensor signal or FREP. So the FREP is sensitive to the thermal change of optical cavity length as well as the sample concentration change. Because the FREP is given by a function of optical cavity length. Right shows the temporal fluctuation of FREP and the cavity temperature, like here, when a sample concentration is constant. The temporal behavior of sensor signal, so here, clearly indicates the dependence on the cavity temperature drift with a sensitivity of 400 Hz per degree. Since such a temperature drift of FREP is larger than the frequency shift caused by the sample concentration change, it reduces the accuracy and reproducibility of biosensing as a temporary fluctuated background. So to suppress this temperature drift, so we focus on the active dummy compensation of temperature drift, which is widely used in the strain sensing. Left shows a schematic drawing of dual strain sensor. So here's a pair of strain gauge with a similar specification is used for the active and dummy sensing strain gauge respectively. The active strain gauge measures the strain and the temperature change, whereas the dummy one measures only the temperature change. So if the temperature change of active and dummy strain gauge are common to each other, the differential signal between them calculated by a bridge circuit is corresponding to the strain signal independent of temperature drift due to the cancelling effect of common mode temperature change. We apply this approach for biosensing OFC by introducing a mechanical sharing dual fiber OFC configuration like here. Similar to the dual strain sensor, so we prepare a pair of fiber OFC with a similar specification for active and dummy sensing OFC. The active OFC measures the sample concentration change and the temperature change, whereas the dummy OFC measures only the temperature change. So if the temperature change of active and dummy sensing OFC are common to each other, the differential signal between them given by frep1 minus frep2 or delta frep is corresponding to the sample concentration independent of temperature drift in the same manner as the dual range sensor. So to confirm the validity of this approach, we first performed the dual-com RI sensing using this setup. We use a pair of linear fiber OFC cavities mod-locked by a saturable absorber mirrors. So a pair of MML fiber sensor without the antigen modification was used for the active and dummy sensor respectively. The active MMI was placed inside the sample cell filled by a test sample of a glycerol solution with a different concentration or RI. On the other hand, the dummy MMI is placed inside another sample cell filled by a standard material, reference material of pure water. And then so the one OFC cavity with active MMI is used for the active sensing OFC, whereas another cavity is including a dummy MMI is used for the dummy sensing OFC. For mechanical sharing dual fiber OFC configuration, a pair of fiber OFC cavity were arranged in an aluminum box covered by an insulating material so that they were affected by similar or common mode temperature drift. And then, so FREP1 in the active OFC and the FREP2 in the dummy OFC are measured by RF frequency counter synchronized to algorithm frequency standard. Finally, so we calculate the frequency difference between them as a delta FREP. We first perform the RI sensing of glycerol water solution. Left shows the sensorgram of FREP1 and FREP2. FREP2 of dummy sensing OFC depends on only the temperature drift, whereas the FREP1 of active sensing OFC depends on both the temperature drift and the sample RI change. So here the sample RI or concentration changes as a step-like behavior, like here. And then so we calculate the frequency difference between them as a delta FREP. Right shows the sensorgram of delta FREP. So in this case, a step-like behavior of sample RI change clearly appeared in the sensor signal. In this way, the active dummy compensation extracts only the RI-dependent delta FREP shift without the temperature drift. We modified the experimental setup for dual-com biosensing. A modification part is here. A pair of MMI fiber sensor with and without the antigen modification are used for the active MMI and the dummy MMI respectively. And then, so these MMI fiber biosensor are placed in the same sample cell filled by a SARS-CoV-2 N protein antigen solution. We perform the detection of SARS-CoV-2 N protein antigen. Left shows the sensorgram of FREP1 and FREP2. Focusing on the FREP1 of active sensing OFC, temperature drift completely spoils the target-dependent shift as a large background signal. However, when we calculate the frequency difference between them, the temperature drift is effectively suppressed, and step-like behavior reflecting the molar concentration of SARS-CoV-2 N protein antigen from PBS 1 attomolar, 1 femtomolar, 1 picomolar to 1 nanomolar clearly appeared. In this way, the delta FREP reflects only the antigen concentration change. From this sensorgram, so we obtain a relation between the antigen concentration and the delta FREP shift, indicated by red plot. To evaluate the validity of these experimental results, we perform the curve fitting analysis with the sigmoidal curve. Because the antigen-antibody reaction in biosensor is represented by the sigmoidal behavior. As a result, the good fitting result was obtained, indicating the validity of dual-con biosensing of SARS-CoV-2 and protein antigen. From this curve fitting result indicated by purple line, we obtained the sensing performance of dual-con biosensing highlighted by yellow color. The limit of detection was achieved to 38 attomolar. Linear range was 34 attomolar to 2.1 picomolar, and the testing time was 10 minutes. For a comparison, the sensing performance for other testing method of SARS-CoV-2, including PCR, are summarized, like here. From comparison among them, only the dual-con biosensing can achieve the limit high sensitivity and short testing time simultaneously. Finally, we summarize the present talk using this slide. So we applied the dual-con biosensing for detection of SARS-CoV-2 and protein antigen. So the active dummy compensation of dual-con configuration significantly suppressed the temperature drift of sensor signal. As a result, so we achieved the rapid detection significantly faster than the PCR and the sensitive detection of attomolar to picomolar antigen close to the PCR. Although one may consider that COVID-19 or SARS-CoV-2 is almost finished, but it is important to note that the proposed method should be available for other virus by selection of antibody, being important as a proactive measure against the unknown and emerging infections. Thank you for your kind attention.